11th grade chemistry textbook from Ethiopia.
Wow.
It even has some basic
That's not something
organic chemistry.
It seems like they cover all the foundational concepts.
Yeah, it's pretty impressive. Now don't worry if you haven't taken a chemistry class in a while.
Right.
We'll break it all down in a way that's clear and hopefully fun too.
I have no...
John Dalton. Need a refresher.
Okay.
Dalton basically said that atoms are the smallest unit of matter.
The indivisible building blocks.
Right, and that all atoms of an element are identical.
Like tiny little clones.
And he said that atoms combine in whole number ratios to form compounds.
So no half atoms or fractions allowed.
Exactly. Dalton's theory was a huge leap forward in our understanding of matter, but how does it hold up today?
Well, some of his postulates have been modified over time, especially with the discovery of subatomic particles.
Yeah,
Thanks
atoms
to scientists
aren't quite...
like Thomson, Rutherford, and Chadwick, we realized that atoms are actually made up of even smaller pieces.
And speaking of Rutherford,
Yes.
his gold foil experiment has to be one of the most iconic moments in the history of science.
It was a real game changer.
Imagine shooting tiny particles at a thin sheet of gold and expecting them to pass right through.
And Bohr's model, with its quantized energy levels, could finally explain why those specific colors appear.
Hey everyone, and welcome to this deep dive. We are going to be trying something a little different for today's episode.
Ooh.
Yeah, so one of our listeners sent us a very interesting textbook to deep dive into, and it's an 11th grade chemistry textbook from Ethiopia.
Wow. That's not something you see every day.
Right. I thought it would be really interesting to kind of dive into it and see what we could learn and, get a glimpse into what the education system is like there.
I'm intrigued. I love seeing how different cultures approach science education.
Yeah, me too. And who knows, maybe we'll pick up some fun facts for our next trivia night.
You never know. Chemistry could be full of surprises.
Exactly. So are you ready to dive into the world of atoms and molecules, Ethiopian style?
Absolutely.
Yeah.
Let's see what this textbook has to offer.
Okay, so before we jump into the hardcore chemistry stuff, there was this little section at the beginning that I just had to point out.
Okay.
It's a whole section on how to care for the textbook.
Oh, wow, really?
Yeah. It's like a whole page dedicated to keeping the book clean and, not dog-earing the pages.
I love that. It shows a real respect for knowledge and the value of education.
Totally. It's like saying, hey, this book is precious, treat it with care.
It's a nice reminder for all of us, really.
For sure. And speaking of respecting knowledge,
Yes.
the foreword of the textbook really emphasizes the connection between education and development, particularly for Ethiopia.
Yeah. That makes sense. Education is such a crucial foundation for any nation's progress.
Absolutely. It talks about how education is vital for Ethiopia's growth. And it's not just about memorizing facts and figures. They're really trying to equip students with the skills they need to succeed in a rapidly changing world.
That's great to hear. Are they incorporating any specific approaches or methods to achieve that?
Yeah, actually, they mentioned some fascinating reforms from 2018. They're really focusing on incorporating indigenous knowledge into the curriculum, which is really cool.
Wow. That's a really holistic approach.
Yeah, right. And they're also placing a big emphasis on technology and even vocational skills.
It sounds like they're really trying to create a well-rounded education system.
Yeah, exactly. They're preparing students for a wide range of opportunities.
It's inspiring to see that kind of commitment to education.
Absolutely. All right, so I think we stalled long enough.
Yeah.
Let's take a peek at the table of contents to get an idea of what kind of chemistry knowledge we're about to deep dive into.
Yeah, let's see what we're dealing with here.
Okay, so it looks like we've got atomic structure, bonding states of matter, reaction rates, equilibrium.
Wow. Quite a comprehensive overview.
It even has some basic organic chemistry.
It seems like they cover all the foundational concepts.
Yeah, it's pretty impressive. Now don't worry if you haven't taken a chemistry class in a while.
Right.
We'll break it all down in a way that's clear and hopefully fun too.
I have no doubt about that. You always make chemistry engaging.
Thanks. All right, so let's start with the building blocks of chemistry.
Okay.
Atomic theory.
The foundation of it all.
I know, right? And we begin our journey with the OG of atomic theory, John Dalton.
Dalton's atomic theory. A classic. It was revolutionary back in the early 1800s.
Totally. So, for those who need a refresher,
Okay.
Dalton basically said that atoms are the smallest unit of matter.
The indivisible building blocks.
Right, and that all atoms of an element are identical.
Like tiny little clones.
And he said that atoms combine in whole number ratios to form compounds.
So no half atoms or fractions allowed.
Exactly. Dalton's theory was a huge leap forward in our understanding of matter, but how does it hold up today?
Well, some of his postulates have been modified over time, especially with the discovery of subatomic particles.
Yeah, atoms aren't quite as indivisible as Dalton thought.
Right, but some core principles still hold true, and the textbook illustrates this beautifully with the law of multiple proportions.
Ah, yes, the law of multiple proportions. It's a great example of how those simple whole number ratios work.
Exactly, the textbook uses water as an example.
Oh yeah, the good old H2O.
It shows that no matter where water comes from, it always breaks down into the same ratio of hydrogen and oxygen by mass.
It's like a chemical fingerprint. You always get 2 hydrogens for every 1 oxygen.
Precisely. It's a simple demonstration of that fixed proportion idea, proving that water is always H2O.
It's a classic example, and it really highlights the importance of those whole number ratios.
Absolutely.
Yeah.
But then came along the discovery of subatomic particles like electrons, protons, and neutrons.
The tiny particles that make up atoms.
Exactly. Thanks to scientists like Thomson, Rutherford, and Chadwick, we realized that atoms are actually made up of even smaller pieces.
And speaking of Rutherford,
Yes.
his gold foil experiment has to be one of the most iconic moments in the history of science.
It was a real game changer.
Imagine shooting tiny particles at a thin sheet of gold and expecting them to pass right through.
Right. Because at the time, everyone thought atoms were like these solid little spheres.
Yeah, like tiny billiard balls.
But instead, some of those particles bounced back.
It was a huge surprise.
A total shock. It completely overturned the plum pudding model of the atom, where everyone thought the positive and negative charges were all mixed up.
Like raisins in a pudding.
Exactly. But Rutherford's experiment showed that most of the mass is concentrated in this tiny, positively charged nucleus.
And the electrons are whizzing around it in this vast, empty space.
It's like realizing the solar system isn't some evenly distributed cloud, but has a massive sun at the center with planets orbiting far away.
A total paradigm shift. And that brings us to the even weirder world of quantum mechanics.
Where things get a little fuzzy.
Fuzzy, yes, but also incredibly exciting. So buckle up, folks.
It all started with the idea that energy isn't continuous, but comes in discrete packets or quanta.
Quanta.
Yeah, it's like saying energy comes in little bundles.
Okay, I think I'm following.
Those were the ideas of Planck and Einstein.
Some pretty big names in physics.
And then Bohr took that idea and applied it to the hydrogen atom.
The simplest atom.
Now, this is a big step in explaining those mysterious line spectra.
Okay, for those of us who haven't encountered line spectra in a while,
Okay.
remind us what those are.
Sure. Imagine passing light through a prism. You get a rainbow, right? A continuous spectrum of colors.
Yeah, like a beautiful rainbow gradient.
But when you heat up an element and look at the light it gives off, you get these distinct lines of specific colors.
Not a smooth rainbow anymore.
Exactly.
Yeah.
Each element has its own unique set of lines, like an atomic fingerprint.
So it's like a barcode for each element.
Exactly. And Bohr's model, with its quantized energy levels, could finally explain why those specific colors appeared.
Okay, I'm listening.
You see, electrons can only exist at certain energy levels, like rungs on a ladder.
Okay.
And when they jump between levels, they emit light of a very specific color.
Ah, so it's like those electrons are singing their own unique tunes.
That's a great way to put it.
Now, the textbook mentions something curious about electron energy.
Oh.
It's negative, by convention. That seems counterintuitive.
I know it trips a lot of people up, but it's really just a way of saying the electron is bound to the nucleus.
Okay.
Imagine a ball in a valley. It needs energy to climb out. The negative sign simply means the electron needs energy to escape the atom.
So a free electron is like a bird soaring high, while a bound electron is stuck in a valley.
Perfect analogy. And when an electron absorbs energy and jumps to a higher energy level, that's called an excited state.
Like it's got a boost of energy?
When it falls back down, it emits that energy as light.
Ah, and that's what creates those specific colors in the line spectra.
You got it. The textbook even shows us how to calculate the energy and wavelength of that light.
Wow, so we can actually predict the color of light emitted based on those energy level jumps.
It's amazing how precise we can be with these calculations.
But then things get even stranger with wave-particle duality.
Ah, yes. The great mystery of quantum mechanics. How can something be both a particle and a wave?
It boggles the mind.
It does. Electrons, like light, can behave like tiny marbles, but also diffract and interfere like waves on a pond.
So are they particles or waves?
Well, the answer is both and neither. Depends on how we observe them. It's one of the fundamental mysteries of quantum mechanics. The act of observation influences the behavior of these tiny particles.
So we can't pinpoint exactly where an electron is.
Right. It's all about probabilities.
Yeah.
Heisenberg's uncertainty principle basically says we can't know both the position and momentum of an electron with perfect accuracy.
So the more we try to nail down its position, the less we know about its momentum and vice versa.
Exactly. It's like trying to catch a firefly in your hand.
Yeah.
The moment you close your hand, you lose track of where it's going.
It's a bit mind-bending, but I think I'm starting to grasp the concept.
It takes time to wrap your head around it. So instead of neat little orbits like planets,
Yeah.
we have these fuzzy clouds called orbitals.
Orbitals.
Yeah, which represent the probability of finding an electron in a particular region.
So it's like a map of where the electron is most likely to be.
Precisely. And each orbital is defined by a set of quantum numbers. Think of them like a zip code for electrons.
Quantum numbers.
Yeah, giving each one a unique address within the atom.
It's like a cosmic filing system for these tiny particles.
I like that analogy. Each electron has its own unique set of quantum numbers that tell us about its energy, its shape, and its orientation in space.
Fascinating. So all of this leads us to how electrons are arranged within an atom?
Exactly. Electron configurations. It's like figuring out the seating arrangement for electrons in a stadium.
Electron configurations.
Yeah. They have to follow certain rules, of course, to make sure everyone has a spot and things stay organized.
So what are these electron seating rules?
Well, there's the off-bow principle, which says we fill up the lowest energy levels first, like filling up the best seats, before moving to the nosebleeds.
Makes sense. The electrons want the best seats in the house.
Then there's Hund's rule. Electrons would rather have their own orbital before pairing up.
Like strangers on a bus choosing empty seats first.
Exactly. And finally, there's the Pauli exclusion principle, which basically says no two electrons in an atom can have the same set of quantum numbers.
So no two electrons can have the same address.
Precisely. Each electron has a unique identity.
Fascinating. And the textbook shows us how to write out these electron configurations both in full and abbreviated forms.
Right. It's like writing an electron's resume, highlighting its energy level and orbital location.
And speaking of resumes,
Yes.
the electrons in the outermost energy level, those are the stars of the show.
The valence electrons.
They're the ones responsible for chemical bonding.
They're the social butterflies of the atom, interacting with other atoms to form molecules.
And their number largely determines an element's chemical properties.
But before we jump into bonding, the textbook takes a detour into the fascinating world of periodic trends.
Periodic trends.
Those are the patterns we see in elements' properties as we move across or down the periodic table.
Oh yeah, like how atomic size decreases as you move across a row.
Exactly. And those trends all stem from those electron configurations we were just talking about.
So the arrangement of electrons dictates how an element will behave.
Precisely. For example, atomic radii, or the size of atoms, generally decrease as we go across a row from left to right.
Because the positive charge in the nucleus increases, pulling those electrons in tighter.
You got it. And then there's ionization energy, the energy needed to remove an electron.
Like how much effort it takes to rip an electron away from an atom.
It generally increases across a row because those outer electrons are held more tightly by that increasing positive charge.
But there are some exceptions to these trends, right?
Yes, the exceptions. They always keep things interesting. They come from the subtle interplay between electron configurations and orbital stability.
So it's not always a straightforward pattern.
Right. They're like little puzzles that remind us there's always more to learn.
It's a reminder that chemistry is full of surprises.
Absolutely. So the periodic table is more than just a chart of elements. It's a roadmap full of patterns and insights into how atoms behave.
And all of this brings us to the heart of chemistry.
Chemical bonding.
What makes atoms stick together to form the molecules that make up our world?
It's all about those valence electrons, those social butterflies we were talking about. They're driven to form stable bonds.
And how do they do that?
Often by achieving a full outer shell of 8 electrons, the octet rule.
The octet rule, the magic number 8.
Think of it like a dance floor where atoms are trying to pair up and complete their set. And there are 3 main types of bonding.
Okay.
Ionic bonding and metallic.
Let's break those down. What's ionic bonding all about?
In ionic bonding, you have a metal and a nonmetal. The metal gives up an electron, completely becoming positively charged, while the nonmetal gains that electron, becoming negatively charged.
So it's like a tug of war for electrons?
And the nonmetal wins, taking the electron for itself. And like magnets, these opposite charges attract, forming a strong bond.
Opposites attract.
The textbook uses sodium chloride or table salt as an example.
Wow.
It walks through the entire process step by step.
Right.
It even shows how to calculate something called lattice energy,
Lattice energy.
which is the energy holding those ions together in a crystal.
So it's like an energy audit for the bond formation.
Exactly. Seeing how much energy is released when those ions come together. But let's move on to covalent bonding, where electrons are shared rather than completely transferred.
Sharing is caring, right? So when does covalent bonding happen?
Covalent bonding usually happens between nonmetals, where the electronegativity difference, their attraction for electrons, isn't strong enough for one to completely steal an electron.
So they decide to share instead of fight.
Exactly. They share electrons to achieve that octet.
Like two roommates sharing a pizza to satisfy their hunger.
And here's where we get to see those Lewis structures in action, those dot diagrams that show us how electrons are shared.
Lewis structures. Those are the ones where we draw dots around the atoms to represent electrons, right?
Exactly. They're a great way to visualize those shared electrons called bonding pairs, as well as the electrons that aren't involved in bonding, called lone pairs. And remember, we can have double or even triple bonds where atoms share more than one pair's electrons.
The textbook uses carbon dioxide CO2 as an example.
Oh yeah, a classic example.
Showing how carbon forms double bonds with two oxygen atoms to satisfy the octet rule for everyone involved.
It's all about finding that stable arrangement.
But things can get a little trickier with resonance.
Yes. Resonance, where you can draw multiple Lewis structures for the same molecule.
So which one is the real structure?
That's the thing. The true structure is a blend of those different Lewis structures. It's like those electrons are saying, we can't decide where to hang out, so we'll just be everywhere at once.
Quantum weirdness strikes again.
The textbook uses the nitride ion NO2 as an example, showing how those electrons are delocalized over the whole molecule.
So it's like they're sharing the electrons across the entire molecule.
Exactly. It's fascinating how complex these interactions can be even at the atomic level.
Right.
But all this bonding talk leads us to molecular geometry.
Molecular geometry.
How those atoms are arranged in 3D space.
So it's not just about what atoms are bonded, but also how they're positioned relative to each other.
Exactly. The shape of a molecule is crucial because it dictates its properties and how it interacts with other molecules. To predict these shapes, we have VSPR theory.
VSPR.
Valence shell electron pair repulsion theory.
Okay, what does that even mean?
It's all about minimizing those repulsions between electron pairs.
Like people trying to maintain personal space on a crowded bus.
Exactly. Both those bonding pairs and lone pairs want to be as far apart as possible.
Okay, so they're pushing each other away like tiny magnets at the same poles.
Made in all sorts of interesting shapes, linear, triangular, tetrahedral, and more.
It's like a microscopic game of Tetris trying to fit those electron pairs together in the most stable way possible.
I love that analogy. And then there's hybridization, where atomic orbitals mix to form new hybrid orbitals that are better suited for bonding.
Hybridization, like mixing different breeds of dogs.
It's like those orbitals are saying, let's combine our powers to make even stronger bonds.
Okay, I could see how that would be beneficial.
The textbook walks us through the example of beryllium chloride, Bl82, showing how those hybrid orbitals lead to a linear shape.
So hybridization affects the shape of the molecule.
But it's not just about the shape. It's also about whether the molecule is polar or nonpolar.
Polarity.
Where electrons are unevenly distributed, creating a positive and negative end.
Like a tiny magnet.
Exactly. And that depends on both the electronegativity difference between the atoms and the shape of the molecule.
The textbook uses water H2O as an example.
Yes, water, the molecule of life.
Showing how those polar OH bonds and the bent shape of the molecule make it a polar molecule.
And water's polarity is the key to so many of its amazing properties, like its ability to dissolve so many substances and its high boiling point.
It's the universal solvent.
But let's not forget those intermolecular forces, the attractions between molecules.
Intermolecular forces.
These are the forces that hold liquids and solids together. They're weaker than the bonds within a molecule, but still incredibly important.
So they're like the glue that holds molecules together in a group.
Exactly. We have dipole forces between polar molecules.
Okay.
London dispersion forces between all molecules.
Yeah, and
then the superstar hydrogen bonding.
Hydrogen bonding, the strongest of them all. It happens when hydrogen is bonded to a highly electronegative atom like oxygen, nitrogen, or fluorine.
Exactly. And those hydrogen bonds are responsible for so many unique properties, like water's high boiling point and its ability to dissolve so many substances.
It's amazing how these tiny attractions have such a huge impact on the macroscopic world.
But let's dive a little deeper into the theory of bonding. The textbook briefly introduces valence bond theory and molecular orbital theory.
Two different theories.
These are two different ways of explaining how those bonds are formed. Valence bond theory focuses on the overlap of atomic orbitals,
Okay.
while molecular orbital theory looks at the formation of molecular orbitals from the combination of atomic orbitals.
So it's like looking at bonding through different lenses, each giving us a different perspective on the same phenomenon.
Exactly. And with molecular orbital theory, we encounter sigma and pi bonds, different types of bonds based on how those orbitals overlap.
Sigma and pi bonds. Sounds like Greek to me.
They're just different ways those orbitals can interact. Sigma bonds are formed from head-on overlap, while pi bonds are formed from sideways overlap.
So the type of overlap affects the strength and properties of the bond.
Exactly. It's like the difference between holding hands and linking arms.
Interesting. The textbook dives into hybridization again, explaining how it can lead to different geometries. It revisits the BCl2 example, showing how spot hybridization results in that linear shape. But let's move beyond individual molecules and consider those vast arrays of atoms, crystals.
Crystals, those beautifully ordered arrangements of atoms or molecules.
It's snowflakes and diamonds.
Exactly. And there are different types: ionic, molecular covalent network, and metallic crystals, each with its own unique properties.
So the type of bonding affects the overall structure of the crystal.
The textbook uses diamond and graphite as examples.
Both made of carbon, but so different.
Both made entirely of carbon, but with drastically different structures and properties due to the way those carbon atoms are bonded.
Diamond is hard and sparkly, while graphite is soft and slippery.
It's a great example of how structure dictates function even at the atomic level.
It's amazing how the same element can have such vastly different forms.
But let's zoom out even further and think about the different states of matter: solids, liquids, and gases.
The three phases of matter.
The textbook reviews their characteristics and explains them in terms of the kinetic molecular theory.
Kinetic molecular theory.
Those tiny particles are always in motion, and their energy and interactions determine whether a substance is a solid, liquid, or gas.
So in solids, the molecules are tightly packed and vibrating in place.
In liquids, they're still close together, but can move around more freely.
And in gases, they're far apart and zipping around all over the place.
Exactly. It's like a microscopic dance floor where the molecules are moving and grooving at different speeds depending on their energy level.
And those gas laws we learned back in school. Boyle's law, Charles's law, Avogadro's law.
Those are all about the relationship between pressure, volume, temperature, and the number of moles in a gas.
The textbook provides clear explanations and examples for each law, reminding us of the ideal gas equation PV, nRT.
Which connects all those variables together.
It's like a mathematical roadmap for understanding how gases behave.
Okay, we've covered a lot of ground. Atomic structure, bonding, even a bit about crystals and states of matter.
But there's still so much more to explore. Like, what happens when these molecules start interacting and reacting with each other?
Stay tuned because we're just getting started with this deep dive.
We'll be back soon to delve into the exciting world of chemical reactions.